Hello, in this video lecture, I'm going to talk about section 1.3, which is about vector equations, okay? So we're going to introduce some notation that's going to be used in this section and throughout the whole course. We'll talk about the difference between the column vectors and row vectors. We'll talk about how to add two vectors, okay? And then we'll talk about scalar vector multiplication. And we'll talk about the algebraic properties of this R-event, which is basically, this is just describing the vector space, okay, that we're in. And then we'll get into linear combinations and this idea of span, okay? All right, so let's start out with some notation. Okay. All right, so if we have, basically, just have a point, okay, and let's assume that we're basically in this plane, okay? And we just have a point here. So typically we just denote this by R of 0. Okay, so that could be some number, okay? Typically that would be like 0, okay? And so there is something called the 0 vector, okay? And turns out that every vector space contains the 0 vector, okay? So we just call this R of 0, okay? And then let's say now, okay, if I were to draw a line to this point, okay, all right, then we get what's called R of 1. So R of 1 is basically just the real number line, okay? And again, the R, okay, R is just standing for real numbers, okay? Since we're only working with real numbers here. So we have R1, okay? And then if we take and extend this idea, okay? So if I have my line here, and if I extend it this way, then now, okay, that allows me or allows us to go in this direction or this direction. Okay, so basically we added a dimension here. Okay, so this is denoted by R2. So this is basically your typical Cartesian plane. Typically this is your x-axis, right? And this is the y-axis. Okay, so that is R2. Okay, so basically this is just the plane. Okay, so we have the line. This is just a point. We have a line and a plane. Okay. Okay. Okay, if we extend on this, again, extending on this idea, okay. All right, so let's assume this is our x-axis and this is the y-axis, okay. All right, and we can still move freely along the x and along the y. So we go horizontal and vertical, okay. But then, right, we need to, right, if we can, right, in order to extend on this, we need to go outside the board here, okay? Either inside, right, the board or facing away from the board, okay? So I'm going to denote that as a dashed line here, okay? And we're going to call it Z, okay? All right, so that pretend like this is facing out towards you, okay? So pretty much like this, okay? So you have X and Y, okay? And then Z is like that, okay? All right. So this is denoted by R3. Okay. All right, so we have a point, just a number, all right, and then we have a line here, okay, a plane, and then basically an extension of the plane, which puts us into 3 dimensions, all right? Now, the thing is, later in the course, we'll talk about the formal definition of a dimension, okay? But right now, when we say dimension, I'm referring to basically referring to the spatial domain that we're in, okay? All right. So if I say a certain vector is in R1, then I'm referring to this space. If I say a vector is in R2, then that means that vector lives in R2. If I say a vector lives in R3, then that vector lives in this dimension, right? In this space, okay? In 3 dimensions, okay? Okay. All right, so then let's now talk about the column vector, right? Column vectors versus row vectors. Okay, so column vectors are typically written, right, as the name suggests, are written in a column form, okay? All right, so for example, let's see, we have U equals to 1, 2, okay? So so again, if we're thinking in terms of X and Y, right, this would be your X value and this is your Y value. In other words, or we can say that this is X1 and this is X2, okay? Here's another example. Okay, we can have 1, 2, and 3, right? So basically the U, okay, U lives in the plane, okay, right, and W lives in R3. Okay. All right, now let's look at these in terms of row vectors. Okay. So expressing the vector U in terms of a row, as the name suggests, we basically write it this way. So in other words, we write it as in terms of a coordinate. Okay, so there's X and there's Y. Okay, and then likewise for W, we're going to get 1, 2, and 3. Okay, right. So geometrically, there's no difference between the column vectors and the row vectors. Okay, they describe the same thing. The only difference is the appearance. Okay, now depending on what kind of calculations we're doing, we may have to work with them we may have to work with these in this form, or we may have to work with the vectors in row form. It just depends on the situation that we have. All right. Okay, so and furthermore, okay, let me just say this. Furthermore, the advantage to this is that we can look at these in terms of coordinates. Okay, so that's the only real benefit. That's kind of the only or I should say, the only benefit of having these vectors in terms of row vectors. Okay, and there are some other uses that are kind of beyond the scope of this class. Okay, but fundamentally, these are the same kind of idea, just expressed differently. Okay. Let's see. All right. So an important statement here. Okay. So 2 vectors. Okay, and let's assume that we're in R2. So basically, we're in the plane. So 2 vectors in R2 are equal to each other. Okay, are equal if and only if. So that's what this means. Okay. If their corresponding entries are equal. Okay. All right, so what does this mean? Okay, basically what this means is that if we have, okay, let's say I have a vector u, okay, and let's say this is u1, u2, and u3, okay, so I'm expressing the vector as a column vector here. And let's say I have another vector, let's call that v, so I have v1, v2, and v3. Okay, if these are, right, if these are equal vectors, then that implies that u1 must be equal to v1, and u2 must be equal to v2, and u3 must be equal to v3. Okay, that's what this statement means. Okay, okay, so if these two are equal, okay, then okay, this is another way. This is the symbol for if and only if, okay, which means that you have a double implication here. So it works both ways. So if this is the case, then, okay, right, this implies that we have u1, okay, equals to u2, sorry, u1 equals to v1. u2 is equal to v2, and u3 is equal to v3, okay? So, all right, so I don't need I'll take out that if statement. Okay? So if, right, these are equal, that's true, that means we have this. If this is true, then that means this is true. So that's what this logical operator means, okay? If and only if, okay? So if this is true, this is true. If this is true, then this is true. Very common. That's a very common thing to see in not only in linear algebra but also in a lot of the math courses. Okay, all right. So notice another thing here: for two vectors to be equal to each other, they have to be the same size, right? That makes sense because when we're comparing things, we have to compare things component-wise. So again, just like with matrices, we always say the rows by columns. Okay, so this is 3 by 1, and this is also 3 by 1. Okay, all right, and this can be right, and this theorem can be extended right in any of these. Okay, by the way, anything beyond right, anything beyond R3. Okay, we can't see. Right, if we're talking about spatial dimension, we can't visualize it. Okay, so anything beyond this point, we have to rely on what's called vector spaces. Okay, because we can't get a grasp, we can't visually see what's going on past this point. So we have to use vector spaces to describe a lot of the properties. Okay, so in fact, we'll get to this later on in the course, specifically in chapter 4. Okay. But for the most part, if you can grasp, right, if you can grasp things at this level, then we can always assume that we can extend on this, we can extend on this, okay? But then it becomes more concrete. We have to rely on these vector spaces, okay? It becomes more important, okay? All right, so this is pretty, this is not too difficult to see, right? Okay, all right. Let's talk about vector addition, okay? Okay, let's go over here. Okay, so for vector addition, all right, so let's suppose let's suppose I have a vector u, okay? And I'm going to say this is equal to, or the components of that vector are going to be 2 and minus 3. And let's say I have another vector, let's call that v, and that is equal to 1, 2. Okay. So the way we add vectors, right, is basically just add the components, okay? And again, in order to add these two, right, in order to add vectors, they have to be the same size, okay? So we have 2 by 1 here, okay? And right, and this is also 2 by 1. So both of these belong to R2, okay? They both live in the plane, okay? All right, so let's go ahead and add those up. Okay, so again, just add the components. So this is going to be 2 plus 1, okay? And for the second component, it's going to be minus 3 plus 2. Okay, so 2 and 1, and then minus 3 plus 2. Okay, and we're going to get 3 minus 1. Okay, so 3 and negative 1. Okay, so that is that is the addition of u and v, which is nothing more than what's called the resultant vector. Okay, all right, which also happens to lie in R2. Not surprising because these two vectors live in R2. So when you add two vectors in the same space, that resulting vector has to be in the same space. Okay, all right. All right. So in general, okay. So in general, the way to add two vectors is just to add them component wise. So if we have u, right, equals to, let's say u1, u2, dot, 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 let's say u of n, so that's a vector in R of n, okay? We have n entries here, and let's let v be equal to this vector, okay? Right, so we have both of these belong to R of n. Okay, so they're the same size. Okay, so the resulting vector that we end up getting, okay, is again just add the components. Okay, so we're going to get u1 plus v1, u2 plus v2, dot, 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 u of n plus v. Okay, and again, because we have n entries here, okay, each of these are numbers. Okay, so this means, right, this belongs to R of n. So again, if you have two vectors that live in the same space, okay, when you add them, right, when you add them together, that vector lives in the same space as the two original vectors. Okay, very important idea. Okay. Okay. All right, so let's see. Let's look at what's happening here. Yeah, let's look at geometrically what's happening here. Okay. And that's also going to illustrate something very important. Okay. So let's go ahead and work with these set of vectors. Okay. So again, right, we're working in R2. So I'm going to call this x1, and this is going to be x2. Because remember, in linear algebra, we typically right? We typically say this is x1 and this is x2. So just think of this as x and this is y, okay? All right, so we have 2 and -3. So I extend this a little bit more. Okay, so let's first look at the vector u. Okay, so again, if we think about this vector as a row vector, then that tells us that we have parentheses 2, comma, -3, and then close parentheses. And so in other words, we can think of this. Okay, that's another way to think about it. And the same thing with this vector. So what we can do, right? We can go ahead and plot those on our plane. Okay? So we have 2 and -3. Okay, so we have down here. Sorry, we get 1, 2, and then we get -3. Okay, so 2, right, in this direction, and then down -3. All right. So let's go ahead and draw our ray. Okay. So that ray represents the vector 2, -3. Okay. Now let's draw the other one. We have 1 and +2. Okay, so here's 1, right, and then we go up 2. Okay, so I'm going to label these. This is, we're going to call this U, and this one we said was V. Okay, now let's plot the vector, or let's plot the this vector, which is which is the result of U plus V. So that's 3 - 1. Okay. So here's 3, and then we have -1. Okay, so I'm going to indicate this in red. So 3 and then down 1 unit. Okay, so let's draw our corresponding vector there. And so that is, again, that's the addition of U and V. Okay, so we sometimes refer to that as the resultant vector of U and V. Okay, now look at this. Okay, all right, geometrically, right, this is what's happening here. Okay. Right, so we have this one, right? So what we can do is we can take this vector, slide it down, okay? Right. Okay, we can take this, slide it down here, okay? And then take this one, right? Okay, sorry, this one, and slide it over here. Okay, so again, what I'm doing here is I'm taking this vector, sliding it down, okay, to here. In other words, that's a translation, right, to there, and then taking this vector and translating it up to here. So where they meet, right? So this one and this one meet here, which happens to be this vector, right? Which happens to be this coordinate, okay? And then we draw, right? We draw a ray or vector from this, right? From this point to this point. Okay, so this is what's called the parallelogram rule. As you can see, this looks like, right? This gives us a parallelogram. Okay. Okay. Okay, parallel. All right. So, all right. So I'm going to write that up here. Okay. So that is basically that is the idea of the parallelogram rule. Okay. So basically that's just a visual way, right? Basically that's just a visual of what's happening when you add two vectors. And also keep in mind, this vector in red, right? That's our resulting vector. Okay, that's the resultant. Okay. They use this term a lot in physics, actually. Resultant. So that's the resultant vector, to be more specific. So that's just the result of adding those two vectors together. Okay. This idea is definitely related to these two concepts. Okay. All right. Let's see now. Okay. All right, so I want to talk about, let's see, need to talk about the scalar vector multiplication. So let's do that here. Okay. All right, so the idea here is, let's say that we have a vector u that lives in R2. Okay, so, and let's go ahead and use the vector 1, 2, okay? And let's C be some real value. So we're gonna let C be equal to, let's say 3, okay? So if I take C, right? If I take the value of C and multiply it with U, okay? This is what we're gonna get. Okay, so you have your constant here. By the way, this is what's called a scalar. Okay. The reason they use that term is just to distinguish it from the vector. Okay. So by definition, okay, you take this value, right? You take this scalar and distribute it into each of the entries of that vector. Okay, so you're going to get 3 times 1, and then 3 times 2. And then that's going to give us 3 and 6. Okay. So as you can see, geometrically, all this is doing is scaling this vector by 3 times. Okay. So in general, okay, if U is in R of n, okay, so meaning that we have this. And again, C, right? If we have our scalar value, okay, and C times U is going to give us, right? We're going to basically distribute the constant through it, right? Through each of these, okay? So make some space here. Okay, so there's C times U. Okay, so we get C times U1, C times U2, and so on. So it's just an extension of, right, of this specific example. Okay. Notice also, right, if u is, right, an n by 1, okay, if n is n by 1, then when you multiply it by the scalar, that still preserves the size of the vector, okay? So the multiplication of the scalar, right, does not affect the original size of that vector, okay? Okay. All right, so we have scalar vector multiplication and vector addition, okay? So with these two, okay, we can combine those two and then talk about, we'll talk about linear combinations, okay, later on. Okay. So let's talk about, let's look at what's happening here in terms of the geometry. Okay, so I'm going to construct our plane. Okay, so this being x1, this is x2. All right, and the original vector we're working with is this vector u. Okay, so we have 1. So let's say 1 here, and here's 2. Okay, so there's what the vector u looks like. So if we take, let's say we take 2 times the vector u, okay? So let's do that here. So we're going to get 3 and 6. Well, that's what we did here. So let's take a look at 2 times the u vector, since we already have that result. So 2 times u is going to be 2 and then 4, okay? So 2 times the vector u gives us this. Okay, so let's plot that. So we have, okay, so we have 2, and then we have 4 here. Okay, notice what's happening here, right? All we did by multiplying u by 2, we basically double it now, right? So this, we have this one, you multiply by 2. Now that total vector, okay, going from here to here, right, is twice, right? So this is twice the distance, okay, right? So this is equal to 2 times this vector, okay? Okay, so I'm going to indicate that here. So here is u, right? And here is 2 times u, okay? Now remember, 2 times u, right? These vectors start from the origin, right? So here's u, and then from here to here is 2 times u. Now let's plot this one, right? 3 times u. So that gave us a vector of 3, 6. Okay, so I'm going to increase this. Okay, so 3, 6 is going to be here. So somewhere there, right? So now you can see, right, the distance from the origin to the point 36, that is equal to 3 of these. Okay. Okay, so we have the vector u, okay, and then this is 2u, and then 3u. Okay. So that's what scalar vector multiplication does. Okay, if you take a scalar and multiply by a vector, then it stretches the original vector. Okay, by whatever that factor is. Okay, whatever the factor c is. Okay. All right. Now, what happens if it's if you have, let's say, 1/2? Okay, well then it's going to obviously take 1/2 of the original vector. So, for example, we have 1/2 of u. Okay. So that's going to be So we get 1/2 of the vector 1, 2. So that's going to give us 1/2, and then obviously 1/2 times 2 will be 1. Okay, so that puts us here. So here's 1/2, okay, and here's 1/2. So it's a little bit hard to see there, but hopefully you get the idea. Okay. 1/2, sorry, so we had 1/2 and 1, so that's going to be up here. All right, let me fix that. Okay, so there's 1/2, and then there's 1, so we're actually here. Okay, which makes sense, right? Because it should be half the original vector. So here's our vector u, and then there's, right, we're halfway, right? It's halfway from here, right, to here. So it's half the distance. So whenever your scalar is, if your scalar value is between 0 and 1, okay, that means it's going to shrink this vector. If it's bigger than 1, it's going to stretch the vector by out whatever the amount is. Okay. All right. So stretching and diluting. Okay. All right. All right. What if u is what if the scalar, what if it's a negative value? Then what that's going to do is going to take what's called the inverse of that vector, which means it's going to go in the opposite direction. Okay. So for example, let's say we have -1 times u. So that's going to give us -1, right? And then -2. So -1, -2, okay? Where this is our vector u. Okay, so let's plot that. So we have -1 here and then -2. Okay. So I'm going to put these on top so that you can see this. Okay, so there's, right, so we have -1, and then we go down -2. Okay, so here. So that vector that I just drew, okay, right, so from here to here, that represents minus, right, that is minus u, right, minus the vector u, okay? Right. Okay, and then so it continues like this, right? If I say -2 times u, then it's going to put us, right, it's going to extend on us in this direction, okay? So when we talk about the inverse of the vector, that's what it means. If I say the inverse of a vector, whatever it is, right, vector v, then you take the negative of that vector. It's going to basically go in the opposite direction. Right? All right. Notice, right, all these vectors, right, no matter what the scalar value is, no matter what value you pick, it's always originating at the origin. Okay, very, very important property. Okay, everything here originates from the origin. Okay, and not only that, okay, for this particular value, for this vector u, everything is along this line. Okay, regardless whether it's 1, 2, 3, 4, 5, right? 1/2. Okay, if I say -1/2 or -5, -100, it's going to be on that same line. Okay. Okay. All right. So. Okay, so let's just write that here. So no matter which scalar we choose, okay, the line always goes through the origin. Okay. Okay. And when I say line here, I mean this is the example, right? Okay, there's a, right, that forms a line. Okay. All right. Okay, it always contains the origin. And when we think about this in terms of vectors, the origin is the zero vector. Okay, right? Okay. All right. All right, so okay, let's get into the algebraic properties of R of n. Okay, so let's first talk about this. Let's talk about what this means, R of n. Okay. Okay, so if n is a positive integer, okay, then R of n basically just denotes the collection of all lists of n real numbers. Okay, so then R of n denotes the collection of all lists of real numbers. Okay, and R again, this R is used because we are working with real numbers as opposed to complex numbers. Okay, all right. So notation wise, that's what we have. Okay. So this is basically, you can think of this as a list, right? It's basically a storage of of real numbers. Okay. So this n, right? This value could be, it could be 0, it could be 1, it could be 2, or so on, right? Okay. All right. Okay, and if, in addition, if u1 is equal to u2, and so on. If all these components are equal to 0, okay, then we have what's called the zero vector. Okay. Okay. So the zero vector. Okay, so sometimes we call these n tuples. So it's just another word for it. Describes the same thing. All right. Let's take a closer look at now, or let's take a closer look at these algebraic properties of organic. Okay. Let's see. All right. Okay, so first we have some assumptions here, okay? So we're gonna we have three vectors here, u, v, and w. Those are all gonna belong to R of n, okay? And then we have our scalar values. Okay? So C and D are elements of real numbers, okay? So those are your, right? So these are basically our scalar values, okay? So the first property, okay, is that if you take u, right, if you take the vector u and add it to the vector v, then we get back this, right? We can get back the same result if we take v plus u, okay? So this is the commutative property. So it's the same idea that you remember from algebra, right? If you're working with real numbers, if you say 3 plus 2, that's the same thing as saying 2 plus 3, right? So 3 plus 2 equals to 2 plus 3. Same idea here, but we're working with vectors, okay? So vector addition is commutative. And that makes sense because of the definition, right? When you're adding these two vectors, you're adding them component-wise. So you're working with real numbers. So therefore, because the real numbers are commutative, right? Therefore, this has to be commutative, okay? All right, the next one is the associative property. Okay? So if I take the vectors u and v and add them together and then add w, well, I can get the same result by adding the vectors v and w together first, and then add the vector u, okay? So no matter which one I add first, right? No matter which group I add first, right? I can add this one, okay, right? Or I can add these two, okay? I can also add u and w together, right? All right, so no matter which pair I add first, I'm always going to get the same result. Okay, so this is what's called the associative property. Okay. Okay, third one. Okay. If I take the vector u and add it to the zero vector, okay. So by the way, the zero vector sometimes, right, sometimes we denote it like this. Okay. So if I take the zero vector, right, so I'm adding nothing, right? I'm adding something, right? I'm adding something to this to u. So obviously then the result has to be our vector u. Okay. And because, right, and using the commutative, right, if we're assuming that right, we already know that vector addition is commutative, so this is the same thing as writing it this way. So u, the vector u plus the zero vector equals the zero vector plus u, which gives both, right? Which gives us the vector u back. Okay. All right. Okay. Next one. Oh, by the way, this is called the identity. This is called the identity property. The reason is because you're taking the vector u and adding it to zero vector, you get back u itself. So it preserves its original identity. Okay. Like same thing, same idea with the real numbers, right? So with real numbers, the identity, okay, right, would be 0, okay, in that case, right? So for example, 2 plus 0 gives you 2, okay? Minus 5 plus 0 is -5, okay? So the identity, okay, the identity property, okay, in real numbers is similar to this one. And this, by the way, the 0 is called the identity element. Okay. So that's the identity element. Okay, next one is if we have u and then plus, if we take the inverse of that vector, remember in inverse, we take the negative of that. And, right, this is the same as, okay, if we say minus u plus u, okay, then basically we get back the identity element. Okay, so this is the same as u, okay, minus u, okay, plus minus turns into a negative, right? So this is going to give us back our identity element. Okay, so this is what's called the inverse property. Okay, right? Because when you take the vector and its inverse, you get back the identity property, right? Okay. So with real numbers, right? If you have minus 4, right? Or let's say you have 4 and minus 4, okay? When you add them together, you get 0, okay? So minus 4, okay? Under addition, okay? Okay, is the inverse of 4, okay? Same idea here, okay? So the inverse of the vector u is just the negative. And so therefore we can say that, right, the inverse of this is minus u, and the inverse of this is, when you take the negative of this, you get back to here, okay? So those, right, so these are inverses, right, inverses of each other, okay? So now later we'll talk about the inverse of a matrix. Little bit different idea there, okay? But because we have a different structure going on, okay? All right, so that is the inverse property. All right, so basically these are focusing on the addition. Now let's look at this, the scalar multiplication. Okay, so if I have the scalar value, okay, so C is our scalar value, and if I multiply it with U plus V, then, right, we can distribute this scalar. Okay. So this, right, this is basically called the distributive property, right? We're distributing over our vectors, okay? Okay. All right. 6. All right, so we can do the same idea here as in 5 with our scalars. Okay, so if we have, let's see, if we have C plus D times the vector U, okay, so we can, much like the same thing as we did here, we can distribute this vector U, okay? So we have C times U, okay, plus D times U. So this is distributing a scalar, right? And this one's distributing a vector, okay? So they're both, right? They're both called the, right? They're both the distributive property, okay? Same idea. Okay. And then number 7, okay? If we have C times D, So something like this. So C times D, or more specifically, let's say we have that. So C times D times the vector U. Well, that's the same thing, okay? I can, instead of multiplying D times U first, I can multiply C times D. And remember, C and D are scalar values, okay? Okay, so it doesn't matter where you start. You can multiply this, or you can multiply C times D, and then multiply it by U, okay? All right, so this is the associate. So basically, this is similar to this one, to this one. The only difference, this is the associative property over scalar vector multiplication. Okay. So that is the associative property for scalar vector multiplication. All right, number 8, last one. Number 8 just says that if we have 1, right, if the scalar value is 1, and if we multiply by the vector u, okay, then we get back the vector u. So this is acting as the identity element under scalar vector multiplication. So 0 here, right? 0 is acting as the identity element, because under addition here, the 1 is acting as the identity element, because 1 times u is just going to give you back u. Okay, so it preserves the vector u. Okay, so this is also called the identity property, where 1 is the identity element. Okay? And remember, this is for scalar vector multiplication. Okay. All right. So with these properties, the reason these are important is because we can, we can work with equations. Okay, and what's called linear combinations. Right. Right. Because if you remember from algebra, okay. Let's go here. Okay. Okay. If you recall from algebra, if you have something like this, okay, let's say 2x plus 4 equals to 0, then how is it that you solve this, right? Well, you basically use those ideas, but for real numbers, right? So the idea is, right, you have to isolate x. How you did that? Well, you use the fact that there is a, right? You use the additive inverse, right? That's what that's called, right? We have an additive inverse of 4, which is -4. So, okay, take -4, okay, on both sides, okay, that gave you 2x, okay. And then how do you isolate the x? Well, you use the, basically use the inverse of 2, okay, which is going to be 1/2, okay. And you did that to both sides, okay. And then you get x here, right? Because 1/2 times 2 gives you, that identity element, which is 1 for real numbers, okay. And then this gives you -2. Okay? So that is, so in essence, that is why these are important, right? That's why these axioms are very important, is because you can do things like this in terms of vectors, okay? Very, very important, okay? All right. So a little bit of flashback there, okay? Okay. All right. So let's talk about, or let's define now what a linear combination is. Okay. All right, linear combinations. Let's define what this is, okay? Okay, so given vectors, okay, V1, V2, V sub n. So we have it. So we're working with a collection of vectors here. And let's assume that we're working in R of n. Okay. All right, so that just means, again, all this means is just that each vector is the same size, right? So they have, so basically right, each vector holds n, right, n elements, okay? And we have scalars, same number. C1, C2, and so on. Okay. Then the vector y, okay. Okay. The vector y, which is going to be expressed this way. So we have C1 times V1 plus C2 times V2, and so on. Okay. So the vector y is written in terms of a linear combination, okay, of V1, V2, and all the way up to Vn. Okay. Okay. So when we say that a vector can be expressed as a linear combination of a collection of vectors, that's what that means. Okay. That's the form that we're talking about. Okay. Okay. So again, we can phrase this way. Okay. So y, the vector y is expressed as a linear combination of V1, V2, and so on. Okay, that's right. So that's what that means. Okay, that's what we mean by linear combination. Okay, and that's nothing more than a right. You're basically taking the scalar multiples of these vectors and adding them together. Okay. Okay. So let's do an example of this now. Okay. So let's say we want to determine, okay, let's see whether the vector b, okay, can be represented as a linear combination of A1 and A2. Where A1 is defined as 1, let's see, 1, -2, -5, and A2 is 2, 5, and 6. Okay, and the vector B that we're referring to, okay, is given as 7, 4, and -3. So we have A1, right, A2, and the vector B. Okay. So the real question, right? So the bottom line is that we're trying to figure out this. Can we find, right, are there a set of scalars, okay? So C1 times A1, okay? And in fact, right, so C times C1 times A1 plus C2 times A2. Now, again, I'm using A1 and A2 here. Those are, right, you can use whatever letters, okay? Right? So can we, right? Okay. Can we find a solution to this? In other words, right, if we can find a solution, that means that B can be represented as a linear combination of this vector A1 and this vector A2, okay? So what does this translate to? Well, this is nothing more, right? This is basically going to give us a system, okay? So we have, right, so we have A1 okay, times or plus this one, right? So here's A1, A2, okay, C1, C2, and then here's our vector B. Okay. So this, right, becomes this, okay? And this is actually, the formatting of this is discussed a little bit more in section 4, okay? So again, if we can find a solution to this system, then therefore B, the vector B can be written as a linear combination of A1 and A2. So let's go ahead and augment these pieces together. So we have 1, 2, okay, and let me see if I have a better marker. Let's see. Okay, so there's our augmented system, okay? There's our, right, so there's our A1, right? There's our A2. That basically that gives us our matrix, right? A, the coefficient matrix, and then there's our B vector, okay? All right, so we go through the row operations, okay? All right, and when you do that, okay, that's in, if you want to see the details of that, it's in my notes, okay? Okay, so putting this into reduced row echelon form, okay? We're going to end up getting this. Okay, and again, to see the specific steps, right? To see those specific row operations, it's in my notes, okay? And I put the notes into the, I'll put the notes into the comments section on the YouTube page, okay? So see notes. Okay, so again, look for the, just look, if you want to see the specific row operations, just see, those are listed in the notes. But the point is, this is what we need. Okay, so remember, here's the column for C1, here's the column for C2. So we have our solution. So C1 is equal to 3, C2 is equal to 2. Therefore, that is our solution, okay? Furthermore, this basically shows us that the vector B can be written as a linear combination of A1 and A2, okay? Right, so we have this, okay? So C1 is 3, so we have 3 times A1 plus 2 times A2 gives us the vector B. Right? So now, if you go back to the idea of that parallelogram rule, right, and the vector addition rule, right, think about this, right? We have 3 times A1, right, plus 2 times A2. So A1 and A2 are in the same because they're both in R3, R3, okay? And therefore, the vector B is also in R3. So they live in this, okay? They live in the same space, okay? And in fact, furthermore, I claim, right, that this vector, right, you have one vector from the origin, another vector from the origin, okay? So let's say you have A1 here, and this is A2, okay? They both, right, they look like this in R3. No matter how you orient it, right? No matter what this, right? No matter, right? It's always gonna form a plane, okay? Right? Okay. Let's just get some sticks here. Okay, but anyway, so let's see if I can do it this way. So that way you can see it more. So you have, let's say this is A1 and this is A2. So it looks, it will look something like this, okay? All right, and it doesn't matter. It doesn't matter what these are, okay? We're living in R3, so you have one in one direction and another in the opposite, or not necessarily opposite direction, but in a different direction, okay? So they form, right? So you can imagine, okay, that if you extend this, this basically forms a plane. And basically what this is telling us is that this vector lives inside that plane. It has to, based on the result, okay? That is our result. So basically this vector B is a linear combination of A1 and A2. Okay, so all 3 of these vectors, what we showed here geometrically is that all 3 of these vectors live in the same plane. And that plane, right? Okay, that plane, which is basically a subspace, okay, which we'll talk about later, lives in R3. Okay, so it's like a piece of paper, right? So it's a plane that lives in 3 dimensions. Okay. All right. Okay. So pretty interesting there. Okay. All right. And you can always check your results, right? You take 3 times A1, right? So 3, okay, plus 2 times 2. So you get 4 and 3 is 7. Okay. You get 3 times -2, so minus 6. Okay, minus 6 plus 10. Okay, that's going to be 4. And then minus 15 plus 2 times 6, so minus 15 plus 12. It's going to give you -3. Okay, so it's a way you can verify your answer. Okay, so now with this example, you can start to kind of appreciate, okay, what this really means. Okay. So if you think about this, A, right? A, and this is discussed a little bit more detail in section 1.4. A is just basically a storage or collection of vectors, of column vectors. And X represents your solution vector. Those correspond to what's called the weights, C1, C2, and so on. And then there's your vector B. Okay. All right. Okay. So if, in general, if you have a vector B here, and if it has a solution, that means, all that means is that, okay, all that means is that the vector B can be written as a linear combination of the columns of A, all right? Okay, column vectors of A. Okay. All right, so we can extend this idea now, or we can talk about the span now. Okay, let's talk about the span. Okay, so here's the definition. So if we, again, if we have a collection of vectors, let's say v1, v2, v of n, okay, that belong to the vector, sorry, but that belong to v, that belong to R of n, then set of all linear combinations of set of all linear combinations of v1, v2, v sub n is denoted, okay, by the span, or I can just write span of v1, v2, v of n. Okay. Right. So that's the idea of the span. Okay, let me elaborate on this. Okay, so what this means is that if so this is connected to this idea. So if we say that y is in the span of v1, v2, v of n, that just means that that vector y can be written as a linear combination of v1, v2, v of n. Okay, it can be written in terms of in terms of the collection of vectors that are given. Okay, so this represents all possible linear combinations. Okay, right, that's all that means. Okay, so it's just a fancy term for this. Okay, so so going back here, so what we can say is that y, okay, y lives in the span, okay, of v1, v2, v of n. Okay. Right. Okay. So it's a set of all, right? So that when we say vector is in the span, that means it can be written as a linear combination. So in general, right, if we say this, okay, if we say span, that means that this basically forms all the possible linear combinations. Okay. So if a vector, so again, if a vector is in the set, okay, so this is just a set, right? So if a vector is in that set, that means it can be written as a linear combination of those vectors. Okay. So going back to this example, right? Because of our result here, we can say that the vector b lives in the span of a1 and a2. Okay. Okay. So this implies, okay, right, this implies that the vector b is in the span of a1 and a2. Okay. So both of these, right? So really, they're really the same kind of idea, okay, but just using different terminology. Okay. 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 All right. So let's look at another example here. So let's look at this. Take a moment to look at this one. So I'm going to let W be equal to, let's say, let's say W1 is equal to 1, 0, 0, and W2 going to be equal to 0, 1, 0. Okay. All right. So let's look at this intuitively. Okay. So again, right. Both of these are in R3, right? However, because we have 0 here, so technically we can visualize these in the plane, okay? Because we have 1 here in the first position and 1 in the second position. So technically this is going to give us, okay? So we have, I'm gonna say that's 1. And, okay, assuming that this is x1 and x2, and then this is 1 up here. Okay. Okay, so we have W, okay, W1 and W2. Okay, so you might have seen these kind of vectors before in Calc 3. These are what's called the standard basis vectors. Okay, so sometimes they're expressed as I and J, right? Okay, and then K, right? K would be 0, 0, 1. Okay, but right now we're just sticking to the basically we're looking at these vectors in a plane. Okay. Okay. So it turns out, right? Very important here. Okay. It turns out that W1, right? It turns out, in fact, if I pick any vector in R2, okay. So any vector V in R2, okay, can be represented as a linear combination of W1 and W2. Okay, so V can be, right, the vector V. You pick any vector in here, okay, then we can easily solve for C1 and C2. Okay. Right, so we have vector V, okay, so we have C1 times 1, 0, 0, plus C2 times 0, 1, 0. Okay. All right. Now remember, we have a 0 here, so that's not going to affect anything. Okay. All right. So any vector, right? Okay. Any vector in here. In fact, what I'll do is I'll just, in order to, we don't need the zeros though, so technically you don't need to write that. Okay. So I'll just take that out for a moment. Okay, so that way it's not so deceiving. Okay. All right, so let's, right, so we have 1, 0, and 0, 1. Okay, so now we're, okay. Okay, so it's a little bit easier for you all to see. Okay, all right, so now, right, we have this. Okay, so any vector I pick, any vector in R2 that I pick, it can be, you can find a solution for C1 and C2. All right, okay, and that's not too hard to see, actually. Okay, and so those, right, we're going to talk about these vectors a little bit later on. Okay, so these are what's called the standard basis vectors. So so the question is, are these the only vectors that make this happen? And the answer is no. There are other suitable choices. Okay, right? There are other vectors that where this will also work. Okay, so the representations are not, they're not unique. Okay, very important idea too. Okay, all right. So what this says, okay, the bottom line here is that because we can pick any vector you choose can be represented in terms of these, right, vectors. Therefore, what we say is that W1 and W2 span R2, okay? W1 and W2 span R2. Okay. Right. So if you see something like that, or if I say something like this, that means all that means is that for any vector I pick in R2 can be represented as a linear combination of W1 and W2. So this will hold true for any vector you pick in this plane, all right? And that's why, right? This is kind of the reason we call these the basis vectors, because they form a base, right? They form the foundation. You can think of these as, these are basically like the atoms, okay, of linear spaces, okay, or the atoms of vector spaces, okay. All right, and we can extend on this idea, right? If you extend to R3, then this will become, right? Then we need to have three, right? 1, 0, 0, 0, 1, 0, and then 0, 0, 1, because we need three vectors, right, to do that linear combination. Okay, so we're going to get back. We'll get into this a little bit later. There's something else that's happening here. Okay, specifically with these two vectors. Okay, so all right. So that is just another example of this idea of, or how this idea of span is used. Okay, all right. Let's look at another one. Okay, let's say I have these vectors. Okay, so I have 1, negative 2, 3, and then 5, negative, let's see, 5, let's see, minus, okay, so it's minus 3, and, well, let's see, negative 13, oh, sorry, negative 13, okay, and minus 3, okay. All right, and we have we have our vector B. Okay. So the vector B here is going to be negative 3, 8, 1. All right. So the question here is, okay, so if we look at this, right? So if we look at, if we take a look at these two vectors, A1 and A2, right? And so if we think about that geometrically, basically that forms a plane through the origin, okay? So we can say that the span of A1 and A2 is basically a plane through the origin. And R3. Okay, so it's like you have a piece of paper in 3 dimensions, and that piece of paper is cutting through the origin. Okay, so the question is the vector B in that plane? Okay, so remember, okay, when we say the span of A1 and A2, we're talking about all the linear combinations that are, right? All the linear combinations of A1 and A2. And again, so this goes back to this idea. Okay, you have A1, whatever this looks like, okay, and A2. They're going to be in different directions, right? Because they're not the same vectors. And also, these are not multiple of each other. Okay, So you have something like this, okay? Okay, we have something, okay, not necessarily, they don't have to be, they don't have to form a 90-degree angle, okay? It's not necessary, okay, but we have something, so we do have something like this. So you can see, imagine, right? There's this, extend this in all directions, okay? Right? Extend this in all directions, and it's cutting through the origin, right? Because both of these start from the origin, okay? So the origin is here, right? I'm holding this at the origin, and imagine a plane, right? So all the linear combinations of A1 and A2 are in this plane, okay? So the question is this vector B, does this vector B lie in that plane? Okay. Okay, so this is what we're trying to solve, right? So we have, can we find, okay, right? Can we find the values of C1 and C2? Okay, so we have C1 times A1 plus C2 times A2 equals to the vector B. Again, I'm using A1 and A2 here. Again, it doesn't matter what the letters are, okay? Those are vectors. Okay. Can we, right? So here's our vector B, here's A1 and A2. Is there a solution, right? Is there a solution to this system? If there is, then therefore that vector B must be in the plane, because that's what the geometry is telling us, okay? All right. So very similar to the previous, to one of the examples we did earlier, okay? All right, with the linear combination example, okay? So this basically we have, okay, so we have C1 times A1 plus C2 times A2 equals to the vector B. Okay, there's our, right, there's our system, not surprising. Okay. All right, so putting this in augmented form, okay, so we have 1, -2, 3, 5, -13, -3, and then -3, 8, and 1. Okay, so there's our augmented system. Okay, there's our, right, there's our matrix A, okay, that's our coefficient matrix, there's our vector B. Okay, now without going through the, right, I'm not going to write up the details here, but those details are provided in my notes. Okay. So the elementary row operations are in my notes. Okay. So going through the steps, we end up getting this. Okay, so we have 1, 5, 0, -3, and then 0 and 0. Okay. So now look at this. Okay. If you look at the last row, okay, there's an issue here. The problem is that, right, there's no solution. Okay, there's no value, right? There's no value such that when you multiply it by 0, it gives you -2. Remember, this just means, right, 0 times, okay, so 0. So basically, just 0 equals to -2, which is obviously false. 0 is not equal to -2. Right? That's a false statement. Okay. Right? So therefore, there is no solution. Right? There is no solution to this problem. Okay. No solution. Therefore, the vector B, okay, is not living in the plane. Right? Okay. So this tells us that the vector B, right? So this vector B, okay, does not, right, does not live in, right, does not belong to the plane. Spanned by, okay, spanned by A1 and A2. Okay, so what is this? So what's happening? Well, again, if you think about this, okay, A1, okay, A2, so if that third vector B is not in the plane, then obviously then it must be sticking outward, right? Okay. Okay, you have your vector here, and then therefore that vector must be, must be not in the plane, right? It must be sticking out either this way or down here. Okay, all right. So that's what this tells us mathematics, right? So the mathematics here tells us basically what's happening geometrically, right? Okay. So it's not in the plane, so therefore it must be sticking outside the plane. Okay. So the vector B doesn't belong, right? So it does not belong in the plane spanned by those two vectors. Right? All right. Okay. All right. So going back, okay. So again, going back to this idea, okay. If that system doesn't have a solution, then that means that vector B, right, doesn't, right? If there's no solution, that means that vector B must not be in the same set, right? Must be not in the same collection as those vectors, as those column vectors of A, okay? All right. Okay. Okay, so one last thing. Okay. And this is going back to some of the geometry. So geometric description of span of one vector. Okay, let's see, I'm calling that V. Okay. And the span of U and V. Okay. So there is a difference here in terms of the geometry. Okay. So, right, so the span, okay. So when we say the span of, if it's just one vector, right? So basically what this is describing is basically the set, okay, of all scalar multiples, okay, of which is the set of points on the line in R3. Okay. Through, and I should say through, okay, through the vector, whatever the vector V is, and the origin. And we're going to remember the origin is just the zero vector, basically. Okay. All right. So, okay, again, so if I have, right, so let's, right, so here, let's assume that we're in R2 here, right? And if we have a vector, okay, let's say that V is equal to 1, 2, okay? So there's my V vector, okay? X1, so X1, X2. Okay. So any multiple, right? Any multiple of this vector, okay? No matter what, no matter if I multiply, if the scalar is 0, if I multiply by a negative value or by a positive value, it's always going to be on that line. Okay, so we say that we say that that result is in the span of this vector v. So, for example, okay, if I say 2 times the vector v, okay, that's going to be 2 and 4. So this vector, this specific vector, lives in the span of the vector v. Okay. All right. So it's just one term of that linear combination, namely the constant, right? The scalar times the vector. Okay. So any multiple, right? Any multiple of this vector lives in the span of that vector. Okay. Regardless, right? Whatever that scalar is. Okay. All right, so we can extend on this idea to this one. Okay, so this is going from a line. Now we have 2 vectors, and just similar to what's happening here, when you have the span of 2 vectors, that forms a plane. Okay. All right, so let's write that here. So if u and v are non-zero vectors, and you'll understand why that is. Why does it have to be non-zero vectors? You'll understand why that is when we get to vector spaces. Okay, so if u and v are non-zero vectors in R3, okay. Okay, again, I'm just using R3 because that's what we're assuming here. Okay, I know that here the vector v lives, when something lives in R2, it's already in, so the plane is already in R3. Okay, so it's just to be consistent. Okay, so the key component here is that v cannot be a multiple, right? It cannot be a multiple of u. So v is not is not a multiple of the vector u. Then span of u and v, okay, basically forms, or we can say forms a plane in R3. That contains both the vector u and the vector v. And must contain the 0 vector because that's where u and v meet. Okay. So probably better to write this way. Okay, that looks better. All right. So in other words, right, if you have 2 vectors, okay, right, let's see, we're in 3 dimensions, right? So we're living in 3 dimensions. Okay, so if you have 2 vectors, right, we're calling those u and v, okay, right, then, okay, and again, u and v are not multiples of each other. If there were multiples of each other, then that would mean, right, that would imply that we have something like this, right? There would be, right, they would be in the same line. Okay, so then we would go back to this case. But right, so we're assuming that these are not multiples of each other. Okay, in fact, this is going to this idea is going to be important later on when we talk about linear independence. Okay, so we have 2 vectors. Okay, that is not a multiple of, right. So v is not a multiple of u. Then the span forms a plane. Okay, so again, all that says is that if I pick any, right, if I pick any vector in that plane, okay, any vector, okay, in that plane that's spanned by this, then that vector can be written as a linear combination of u and v, okay? So this is a direct, so this implies that okay, or and if the vector y is in the span of u and v, then this, right, this just means that the vector y is equal to C1 times u plus C2 times v. Okay? So from now on, every time I say span, okay, or if you read the term span, this is right, this is what should come to mind. Okay. Likewise over here, right? If I say that if you have a vector y that belongs to the span of v, okay, okay, so if I have a vector that belongs to the span of v, this, okay, implies, okay, now because we're working with one vector, so then we have that y is equal to right, some multiple of that vector, okay? So we have one vector, this is the situation, right? If you have two vectors, right? And then so it works, right? So then we can expand on this idea, okay? All right. So hopefully you can see the difference now, right? Between the span of one vector and the span of two vectors, where these vectors are not multiples of each other, okay? So I'll go ahead and stop here, okay? That basically concludes section 1.3. And this is all going to be used later from now on throughout this chapter and beyond. Okay. All right. So I'll stop here and I'll see you all next time.